So if you've landed on this video, chances are you're either thinking about or already working towards a degree in either physics or engineering, and it's not a decision to take lightly. Even though these two fields can look almost identical from the outside, the one you end up choosing could seriously shape the kind of work you do after graduation, and frankly, what you take home in your paycheck. I've earned a degree in mechanical engineering, and I had to take a lot of physics classes to get there, so I have been exposed quite well to the underlying philosophies behind both fields. In this video, we're going to dig into what actually separates these two degrees from each other, and what kinds of careers each one tends to open up. But before we zoom in on either field separately, let's talk about the fundamental difference in how they think. Because even though physics and engineering can seem nearly identical, they're actually rooted in completely different philosophies. Physics, at its heart, is asking why. Engineering, on the other hand, is asking how. A physicist wants to understand why objects behave the way they do when they collide, or why planets follow the orbital paths that they do. An engineer is concerned with how to actually build a rocket capable of reaching orbit, or how to construct a bridge that won't fall down. Another lens through which you can see this is how each field actually drives progress. Physics tends to chase the fundamental laws of the natural world, sometimes purely for the sake of understanding, even when those discoveries have no obvious real-world use yet. Engineering, meanwhile, takes those very laws and figures out what can actually be built with them. You could think of it as engineering picking up where physics leaves off and turning understanding into something tangible. Alright, so let's look at each of these fields on their own, starting with physics. I've covered this before, but the key thing is to know that when you start a physics degree, pretty much everyone follows the same path at the beginning, regardless of what area you want to specialize in down the line. Whether you're aiming for astrophysics, quantum physics, nuclear physics, or medical physics, your first year is going to look broadly similar. Forces, energy, motion, and the core building blocks of how the physical world behaves. As you move through the degree, things start to branch out. You'll pick up modules on topics like general relativity, high-energy astrophysics, quantum mechanics, special relativity, depending on where your interests take you. One of the things that I generally loved about studying physics was just how wide-ranging it is. Because everyone goes through that common foundation at the start, you naturally get exposed to areas you might never have thought to seek out on your own. For me, I definitely enjoyed Newtonian mechanics, something I found brutally mathematical and intense, but completely fascinating despite the fact that I came into the degree primarily interested in astrophysics. The breadth of topic also means that you come out with a surprisingly wide skill set. Different areas of physics develop different capabilities. Quantum mechanics pushes your mathematical thinking hard, while astrophysics pulls you toward programming and data analysis as you would with telescope data. What this means in practice is that physics graduates tend to be remarkably employable across a huge range of sectors. You'll find physics grads working in engineering, finance, tech, and education, and that's because the skills they develop are genuinely sought after in all those areas. We're talking about mathematical ability, coding, data analysis, data visualization, and the ability to tackle complex, open-ended problems. These aren't niche academic skills. They're things employers genuinely want. One skill in particular that I think has made a real difference in my own career is that physics teaches you how to think. Not in a rigid, formulaic way, more in the sense that conditions you approach unfamiliar problems creatively and come up with solutions that aren't obvious. That kind of thinking is extremely valuable to employers, even outside of science. Now let's be real about the downsides, because there are some. Here's a truth that doesn't always get said out loud. If you graduate with a physics degree, there's a pretty good chance you will not end up working as a physicist. That's not because the degree isn't valuable. It absolutely is. But because there are far more physics graduates than there are research positions available. Unless you're planning to continue into a PhD and pursue an academic research career, the odds are that you'll end up in tech, finance, or some branch of engineering rather than doing physics professionally. In fact, only about 9% of physics graduates go on to work in a scientific field after finishing their degree. That's worth keeping in mind so your expectations are grounded in reality. There's also the matter of how abstract a physics degree can feel at times. It can even come across as disconnected from anything practical. Think about it this way. You might develop a deep understanding of why a rocket is physically capable of escaping Earth's atmosphere, but you never actually get to work on the propulsion system or the navigation system that makes that happen, because that's an engineer's domain. If you're someone who gets a lot of satisfaction from building and creating real things, you might find the theoretical nature of physics a bit frustrating at times. That said, physics remains a genuinely absorbing subject. The range of material you cover keeps things interesting throughout your degree, and the ability to steer your focus as you progress means you're not stuck studying things that don't excite you. Now let's discuss engineering. The first thing worth flagging here is that engineering isn't really one degree. It's more of an umbrella term. Unlike physics, where everyone begins on more or less the same track and gradually specializes, in engineering you typically choose your specialism from day one. That might be mechanical engineering, civil, electrical, aerospace, nuclear, or any of several other branches. I'm not going to go into deep detail into the curriculum of each of those specific paths, since I just don't have time to talk about them all right now, but what I can highlight are the kinds of differences you'd see between engineering and physics when both touch on similar subject matter. Take thermodynamics as an example. In an engineering degree, thermodynamics is typically approached through the lens of an application. How do we use our understanding of heat and energy transfer to design an engine, keep a power plant from overheating, or build an efficient refrigeration system? In a physics degree, the equivalent subject, thermal physics, digs into what's happening at the level of individual particles, statistical mechanics, entropy, and the theoretical foundations of how energy behaves. The subject matter overlaps, but the angle is completely different. And you'll see the pattern repeat across plenty of other topics. Engineering courses do still involve a solid amount of mathematical, physics, and theoretical content. It's not all hands-on work, but the underlying goal is always about applying that knowledge to build something functional. The shift is from understanding the world to just figuring it out and improve how we live in it. One of the clearest advantages of an engineering degree is the job market. Put simply, there are a lot more engineering jobs than there are physics jobs. And because engineering degrees are already specialized, you graduate with a skill set that maps pretty directly onto specific roles. A mechanical engineering graduate applying for a mechanical or aerospace engineering position is going to be in a much stronger spot than a physics graduate applying for the same role, because they'll have the engineering-specific knowledge and training that a physics degree just doesn't cover. That specifically also tends to make career entry a bit less confusing. You know what you've studied, you know what you do, and that makes it easier to identify where you fit in the job market, rather than having to work out which industries will actually value your more generalist background. Another thing that works in engineering's favor, particularly when it comes to long-term career stability, is that engineers are needed almost everywhere, pretty much indefinitely. Energy infrastructure, water systems, transportation, these things need engineers, consistently, across every country and every era. The demand for research physicists is inherently more variable. And this sustained demand is reflected in salaries. In engineering, graduates constantly rank among the highest paid degree holders across most countries. But the specialization that makes engineering so career-ready also has a downside. You're locking in your direction from the start, which means if you're partway through the degree and you realize that you actually want to be doing something different in engineering, switching can be more complicated than it would be for a physics student changing their area of focus. If you're an electrical engineering student who realizes that they're much more drawn to civil engineering, you do have a problem on your hands. A physics student who starts off interested in nuclear physics and shifts toward astrophysics is a far simpler transition. There's also something that might bother some people who genuinely love understanding things at a deep level. Engineering can sometimes feel like it stops asking questions too early. It cuts the chain of why at some point and jumps straight to the how do we do this. If you're someone who wants to keep pulling at the thread, who wants to understand things all the way down to the most fundamental level, you might feel a bit shortchanged by an engineering curriculum compared to physics, which is genuinely committed to asking why at every single step. One more thing I'd mention from my own personal experience, something that doesn't really come up in university prospectuses, is that early in an engineering career, it's pretty common to feel like a very small part of a very large machine. It's rare for a new engineering graduate to be working at the project level on anything. If your dream is to design spacecraft, the reality is that you're probably going to spend your first few years working on a small subsystem, maybe something as specific as a bracket that holds two components together. That's just the nature of large-scale engineering projects. And there's nothing inherently wrong with it, but it can be a bit of a reality check if you pictured yourself doing big-picture design work from day one. In contrast, physics research, especially at the PhD and postdoctoral level, tends to give you considerably more ownership on the direction of your work, even relatively early in your career. So, physics or engineering, which ones should you go for? The honest answer is that it depends entirely on you. What you're genuinely excited by, what kind of work you want to do, and what kind of future you're working toward. The reassuring part is that either way, you'll come out of your degree having developed serious critical thinking skills, the ability to tackle hard problems, and knowledge that sits at the frontier of what humans currently understand and can be built. The question isn't which degree is objectively better, it's which one is right for you and where you want to end up. I hope this video gave you something useful to think about. If you know someone else who's weighing up the same decision, feel free to share it with them. Thanks so much for watching, good luck with your studies, and I'll catch you in the next one.